Hello, good evening.
Good evening, sir.
Okay, so who is that Pratyay? Who is this Federation of Terra? Please use your real name. Niharika Charumati Avnish. Okay.
Rahul Naveen, sorry, I've joined using an alternative account. I will
Who is
log
this?
Rahul Naveen from
Rahul.
MPSP.
All right.
Log in using my other account. Sorry, sir.
Sure. All right. So I guess we'll get started. I will just share the screen. You can start solving that problem. You would have already had, I hope you would have attempted it before. I told 31 to 44 of the DPP will do, right? The subjective questions. So let me share my screen. Window, capacitance, share. Okay. So I hope the screen is visible to everyone. This is that question number 31 from the DPP. Find the equivalent capacitance between P and Q. And as you can see, this is C1, C2 on the left, and then C2, C1. And this is C3 in mid. So this is an unbalanced Wheatstone bridge. And you need to find the equivalent capacitance. You might have done in your classes also. So start solving this, and hopefully others will also arrive soon. So you would get a lengthy expression. So I don't expect you to type it out in the chat. Just say whether you're done or not, right? Just say done once you're done. If you can type it out, that's fine. Okay, it's 6:10 now, so almost 10 minutes have been given for this problem, those who arrived at 6, that is. So I'll start the problem for you guys. You complete the calculation, okay? So in problems like this, it's always useful to connect this P and Q to a battery. So let's say I take a battery and connect to the terminals P and Q. Let's say there is some EMF E provided by the battery, okay? As a result of it, some charges will deposit on these capacitors. Let's assume there is some positive Q1 on this charge, on this plate of the capacitor. So this becomes minus Q1. Similarly, let me assume some positive Q2 and minus Q2 as such on C2. Okay. Then by symmetry, looking at the problem, if I just reverse the polarity of the battery, I should get identical charge distribution on this C1 and C2. So just invoking symmetry in this problem, I can assume, remember, this basically whatever charge Q that you have drawn from the battery gets split into Q1 and Q2. The same amount of charge should combine to form Q again. So this will become minus Q2 plus Q2 minus Q1 and plus Q1. Okay, directly I can write down. I don't need to assume any other charge, but just by looking at the setup here. Okay, this is diagonal symmetry. Now let me assume on C3 there is some Q3 and minus Q3 as such on the plates of C3. Okay. What I will do is, so first we'll apply the junction law. This charge Q gets split into Q1 and Q2. So I'll write Q equals to Q1 plus Q2. That gives me one equation from the junction law at P or Q. The junction law at A will give me, just add this conducting island from here to here. The net charge should be 0 on that conducting island. So that gives me minus Q1 plus Q2 plus Q3 equals to 0, or Q1 equals to Q2 plus Q3. Q2 plus Q3 gives you the second equation. Write down the loop law. Now you can either use this law, this loop, or this loop. Both will give you identical results. So use any one of these loops, right? Let's call it loop 1. Loop 1, I apply the Kirchhoff's loop law. I'll start from, let's say, point P, this point, go around in this clockwise fashion and come back to that point. So what will I get? The first term would be, we're going from plus to minus, so it will be minus Q1 by C1, right? Then you're going from plus Q3 to minus Q3, so that will be minus Q3 by C3. And then you're going from minus Q2 to plus Q2, so it will be plus Q2 by C2. This is equal to 0 because you've come back to the same point. That is your loop law. Perhaps you can write it, well, let's just skip this as it is, or let me write Q2 by C2 equals to Q1 by C1 plus Q3 by C3 as equation number 3. Okay. And the last equation you can write for this outer loop here, right? Let's say I start from this point, I have a cell, then I have C2, C1, and then back to that same point. So for the second loop, I'll write it here itself, loop 2, I'll get E minus Q2 by C2 minus Q1 by C1 equals to 0. Or that just gives me E is equal to Q1 by C1 plus Q2 by C2. That gives me equation number 4. Okay. what you need to do is, in order to find the equivalent capacitance, you just take what is the charge that is given to this circuit and divide by the potential difference that you have provided to the circuit. So C equivalent of this this combination is just charge by the EMF of the cell. Okay. So basically, you need to find out what is this Q in terms of E, right? And basically, whatever will be left behind will be your equivalent capacitance. So you have 4 equations and 4 unknowns, right? Q1, Q2, Q3, and Q are the unknowns. If you try to solve them in terms of E, and then if you do Q by E, you will get your equivalent capacitance. So I have written down the 4 equations. Now please try to solve it. If you're done, please say done or try to type it out if possible. Okay, I still don't have any response. So let's wait for 3 more minutes to solve this question, and then I'll solve.
Sir,
Yes.
sir, after this, could you discuss some of the objective questions in the DPP? Like the ones that we hadn't done last class. I had a doubt in few of them.
Okay, so what? So today I have said that we will do the subjective questions, which might take time. What you can do is you can post the particular questions in the doubt group, okay? And then I'll try to give a response there. Is that fine?
Yeah.
Okay, sure. Good. Okay, so it might be a little bit tedious to solve, but once you just follow all these equations, you should be able to solve it. So I'll begin writing the solution. Just you guys can write later. Right, so we want to write, let's write Q1, Q2, Q3, we need to write in terms of Q, okay, and then Q in terms of E. So yeah, I'll first try to eliminate Q3. So from this, let me use a different pen, I suppose. So this I can write it as Q3 equals to Q1 minus Q2, okay? And I'll substitute this Q3 into the third equation. So what does it give me? It gives me Q2 by C2 equals to Q1 by C1 plus Q1 minus Q2 by C3. Fine. Now I'll separate Q1 and Q2. That gives me, let's write Q2 on one side. So Q2 into 1 by C2 plus 1 by C3 equals to Q1 into 1 by C1 plus 1 by C3. Correct? Now let's take the LCM. I'll get Q2 into C3 plus C2 by C2 C3 equals to Q1 into C1 plus C or C3 plus C1. It's the same thing by C1 C3. We'll cancel C3 here. We'll get Q2 equals to, let's cross multiply and write it. So Q2 is equal to C2 C3 plus C1, or let's say C1 plus C3 divided by C1 into C2 plus C3 times Q1. Okay, we got one relation here between Q1 and Q2. Okay, very good, Ayan. Now, we got Q2 in terms of Q1, and from that we can find out what is Q1 in terms of Q. So let's substitute this Q2 into the first equation. Okay, so I have Q equals to Q1, if I take common, 1 plus this expression, C2 into C1 plus C3 divided by C1 into C2 plus C3. So what will I get? Q1 into, the denominator is C1 into C2 plus C3. And let's just expand everything. I'll get C1 C2 plus C1 C3 plus C1 C2 plus C2 C3. Correct? So this gives me Q is equal to Q1 times, what is this factor? Or let's try the other way around. I'll get Q1 equals to C1 into C1, C2 plus C3, C2 plus C3 divided by, I have 2 C1 C2 plus C3 into C1 plus C2. Correct? Times Q. Correct? So I got Q1 now in terms of Q. Similarly, what is Q2? You need to basically divide by this factor and multiply by this factor. If you divide by this factor, that is nothing but the denominator, the numerator here, right? So that numerator vanishes, and then you multiply this numerator over here. So you will get Q2 is nothing but C2 into C1 plus C3 divided by the same denominator here, which is 2 C1 C2 plus C3 into C1 plus C2 into Q1, Q. Correct? So we got Q1 and Q2. Substitute this Q1 and Q2 into the fourth equation. Right? So I'll get E is equal to Q1 by C1. So just divide C1 here. Both have the same denominator, so directly I'm writing C2 plus C3 plus Q2 by C2, you divide C2 here. So you'll just get C1 plus C3 divided by the same denominator, 2 C1 C2 plus C3 into C1 plus C2. times Q. Now you rearrange, what do we need? We need Q by E. So therefore, your C equivalent, which is Q by E, is nothing but 2C1 C2 plus C3 into C1 plus C2 whole divided by the numerator here, which is C1 plus C2 plus 2C3. And that is your answer. Okay. So I hope you were able to follow what I did here and do it on your own if you haven't done already. Do we have more responses? No. Okay. Let's move on to the next question. We've spent more than enough time on this one. It's just algebra, right? 4 equations, you just need to solve. Right. Moving on to the next question. Right. Just look at the expression. You can, it's there. The answer is there in your DPP also. Right. Moving on to question number 2. Please try to solve this. I'll give you 4 minutes for this. Actually, you don't need 4 minutes, but still, just to think. Okay, good. We already have one response. Okay. Please work it out. Electric field is given as a function of y coordinate. So from that you need to find out the capacitance, right? The capacitance of these two conductors. Right, 4 minutes are up, I believe, or almost up. We can look at it. This is a relatively simple problem. What do you need to do? Electric field is given as a function of this variable y, right? And we know the relation delta V equals to integral of minus E dr, right? It's E dot dr actually, but we'll ignore all the curve and all. We'll assume the electric field and we'll, to be like straight line here, we'll just integrate from here to here, okay? Near the center at x equals to 0 where it is nearly parallel. So your dr is just dy, right? You're moving along y axis. So this integral just turns out to be e into dy, okay, from 0 to d. And I suppose we can ignore the minus sign because you're going from higher potential to lower potential. Then you can write it as your potential decreases, right, if you go up. And when you're doing delta V, so essentially, when I say delta V, this is V minus minus V plus, right? So if you do, let's say the potential difference here is V, right? So this is V is V plus minus V minus, okay? And this delta V over here in this definition is V minus minus V plus, okay? So from here we'll get V is equal to integral e dy from 0 to d. And this you can easily integrate. It's just a polynomial. Q by epsilon naught a is a constant. You can keep it outside. Integral 0 to d of 1 plus by square. So this is nothing but q by epsilon naught a into d plus b d cube by 3. Correct? Now you know that capacitance is charge q over potential difference v. So if you do q by v, you will get epsilon naught a by, you can take d common and write it as 1 plus b d square by 3. So that would be your answer. Okay. I think this should be clear for everyone. If not, please ask if you have any doubts. Fine. So let's move to the next problem then. If there are no doubts, just simple integration of a polynomial. Most questions, you just have to use this relation, right? Wherever field is given or you need to use a field, to find the potential difference, you'll just use this relation and we'll get Q by V will give you the equivalent capacitance. Right, moving on. Something similar you have to do here also. I hope the question is visible. I'll zoom it in further. So please work this out. So once you get the first question, the other questions will follow from it. But I'll give you 5 minutes to solve this question. Right, so you can answer part wise. Question part 1 you can answer first. That should take only a couple of minutes. Yeah, so there will be a plus minus sign somewhere. Ln R2 by R1 would be positive, right? Because R2 is greater than R1. So
Yes.
yeah, it doesn't matter. It's the magnitude is same.
Magnitude will be different no? If
Yes.
if you ln R1 by R2 is not, the magnitude won't be same as R2 by.
It will be, right?
Acha,
So it
हाँ,
is
it will be
negative.
minus. हाँ, yeah.
So let's just look at the first part, and then meanwhile you can solve second and third part. The first part, let's draw. Again, we are assuming this length is much greater than the gap between the cylinders, right? And also bigger than the radii of the cylinders also. So you can assume this to be similar. You can use the field, the result for infinite line of charge or infinite cylinder of charge. So what we're doing here is, if you look at it top down, you will see two concentric cylinders. That is very good. Okay, somewhere here would be the central one. So this is R1 and this is R2, right? So what we'll do, we'll just take the field at any R between the two cylinders, right? You choose a Gaussian cylinder of radius R. The field inside, you can find the using Gauss law, that will just give you E is equal to lambda by 2 pi epsilon naught R, right? That's the field for an infinitely long line of charge. Here lambda would be Q by the length of the cylinder L. So that will be Q by 2 pi epsilon naught L into R, correct? Now, if we integrate this, we will get the potential difference, right? So we'll integrate this field from R1 to R2 or R2 to R1, whichever way you want to go. So inside is positive, outside is, this is positive, this is negative. So that means the field goes from in this direction, radially outward, which means the potential difference of the inner cylinder would be greater than the outer cylinder. So when we write down integral, delta V is equal to minus EdR, and I'm doing this from, when I say delta V, I'm already doing it from my R1, my R changes from R1 to R2, right? R1 to R2. So in that case, this delta V would be negative, okay? If you want to do, you just take the magnitude of that if you want to find the higher potential minus lower potential. So if you write it like this, you will get Q by 2 pi epsilon naught LR into dr. So all these are constants. I'll keep it outside the integral. R1 to R2, I can let it just be R1 to R2. And minus will remain because we are doing V minus minus V plus. Okay. So this here is actually V minus minus V plus. Okay. So what is this? Minus Q by 2 pi epsilon naught L. This is 1 by R. 1 by R integral is ln R. Plugging the limits gives me R1, R2. That gives you, and I'll write V plus minus V minus as, get rid of this minus sign, write as 2 pi epsilon naught L into ln upper limit minus lower limit will give you R2 by R1. Okay, I hope this is clear to everyone. Just integrate the field to get the potential difference. Okay, so let's go back to question part 2 now. Compute the electrostatic energy stored in the capacitor. So has anyone done that? Electrostatic energy stored in the capacitor. Which formula will you use here? We have to find U in the second part. This is the first part. Okay. Third answer is there from Charumati, which is KQ. What is the third question asking even? L square. Right. Okay. That is correct. Please solve the second one also. I'm curious how you got the third answer before the second one, but maybe you can.
No, sir, I did solve the first and second one, but I got the same answer as the everybody else, so I didn't really type it.
No. The second answer has anyone written?
Yes, sir.
Where? I've only seen the first.
So the second is there.
It's okay. You write down the second one also. It's similar form, but dimensionally it will be different, right? Because they're asking energy. Yes. KQ square by L into ln R2 by R1. Correct. And once you get that, then you differentiate with respect to L to get the force. Because L is the only variable in the third case. Good. Okay, so again, typing it might be slightly tedious. So let's just start solving this. Electrostatic potential energy, I can use the formula here as integral of U into D. This V, I can write it as D tau, where this is the volume element. And this is the, what is it? It's the electrostatic energy density. Energy density. We know what is the formula for small u. Small u is given by half epsilon naught E square. There's no dielectric anywhere, right? Yeah, so it's just half epsilon naught E square. And what is this volume element? Since we are looking looking at cylinders, we will take a cylinder of radius r and we take a thickness of dr around it. So this thickness, let it be dr, and there is radius r. So what will be the volume of that thin cylindrical shell or thin cylindrical, what do you call it? Thin cylinder, let's just call it. So its surface area, the curved surface area would be 2 pi RL multiplied by the thickness dr. That gives you the volume of that thin cylinder, right? So that volume element d tau is nothing but 2 pi RL, that is the surface area, curved surface area, multiplied by dr, the thickness, that gives you the volume of that shell. So this gives you U is equal to integral of half epsilon naught E. We just found out what is E, right? I mean, it's given what is E. So let's substitute that here. I'll get Q square by 4 pi square epsilon naught square L square R square. So Q square by 4 pi square epsilon naught square L square R square. R square. That is your E square. Then multiplied by d tau, that gives you 2 pi R L dr. and you integrate it from R1 to R2 or R2 to R1, whichever gives you the positive value, right? So this is energy, so we'll take it as a positive value here. I can cancel a few things here. I can cancel this 2 and this 2. Epsilon naught, pi, R, L, and L. What am I left with? Q square by 4 pi epsilon naught L into integral 1 by R dr between the limits R1 and R2. So it's the same integral as before, only this factor, there's a Q square now, right? And there's one more factor of 2 in the denominator. So this would be Q square by 4 pi epsilon naught L, ln R2 by R1. Okay? I hope this is clear enough. Right? Solving it is easy enough. Just need to understand how to integrate this, right? Energy density times volume gives you the energy. And you need, because the field is not constant, right? It's a radial field, depends on the radius, depends on the distance from the reference point here. So you need to integrate over this volume. Okay. Once you have the energy density, this gives you the answer for the second part. You have the energy. Now you can find what is the force when you raise the inner cylinder by a small distance delta L. Okay. So when you raise the inner cylinder, the distance between the two cylinders will not change. Correct? The charges on the cylinders will not change. Only the length, the common length that they have will change. Correct? So the variable becomes this capital L becomes the variable here. You know the relation between force and potential energy for a conservative force. So we can use F is equal to minus du by dl here. L is the variable. So what will I get? Remember, all these are constants. R1, R2 doesn't change. Q doesn't change. So only variable here is L. So that gives you derivative of this is minus 1 by L square. I don't know why they've kept the minus in the answer, but it doesn't matter. So what will I get? Q square by 4 pi epsilon naught L square into ln R2 by R1. Okay, that would be your force. Derivative of 1 by L is minus 1 by L square. So this would be the force. That would be the answer for part 3. Okay, I hope this is clear. Once you get the energy, then it's just a straightforward differentiation with respect to L. Let's move to the next problem then. Okay. Okay, let's try to solve this one now.
So the third part,
Yeah.
the third sub question, how do you?
Yeah. Which
Okay.
question you're asking? This
There was
question
a
right now?
There was a third sub part to that question, right? So
That's
how
what we
do you-
just solved, right?
Yeah, but could you? No, that wasn't.
Yeah. So this internal cylinder is raised by some small distance, right? So when you raise it up, what changes in that capacitor? The common length between the cylinders will change,
Yeah.
right? Everything else, R1, R2, Q1, Q and minus Q, everything remains same. Only thing that changes is the common length between them, right? So that L becomes your variable. We can write force as the derivative of potential difference with respect to that variable L.
Okay.
Okay, so directly we'll get the answer here. So this would be like an attractive force, which will try to, so you have certain energy associated with the capacitor. When you try to change that energy, the system wants to minimize that energy, right? Whatever the energy is there. So it will try to bring it back to that original position. It will actually start an oscillation here. That's a different problem. Let's not worry about it. But basically, it will be an attractive force. Maybe that's why that minus is there in the final answer, in the solution that is given. Okay. Right. So let's move to the next problem. I hope this is visible to everyone. 3 concentric shells of radius A, B, C. Let's draw 3 concentric shells. Okay, let's assume these are 3 concentric shells of radius A, B, and C. A is connected to, means the first one is connected to the outer one. Inner one and the outer one are connected through a hole in the second one. So let's draw a hole here and then connect the two, something like this. So the first and the third one are connected, and the second one is grounded, right? Connected to earth. Let's just say ground is here itself. Let's not draw more holes. So the second one is grounded. First and the third are connected by a thin conductor. So find the capacitance of the system. Please work it out. Did someone join just now?
Yes, sir. I was unaware there was a class today, so I just joined.
Okay. Okay. Right. Do we have any responses? I don't see any. Okay. Right. So, in the interest of time, since we have some more questions, let me start the problem. I'll leave the, and then I'll ask you to complete the calculation. So, before we solve this particular problem, what I would ask you to do is just let's look at two concentric circles. You would have done it in your classes also, in your regular classes. Right. So, if I take, let's forget about this for a second. Let's use a different pen, I suppose. Oh no. Sorry. Color I need to change, right? Let's use purple, I suppose. All right. So let's just look at two concentric shells, okay, where the outer one is grounded and the inner one is given some positive charge, okay, positive charge. It will induce a negative Q on the shell, outer shell. And what would be the capacitance? Let's say the radii are A and B. Essentially, I'm looking at this inner part of the shell, right? I want to look at the capacitance of just the inner part of radius A and B. Let's forget about the outer shell for the time being. Okay. Now, what will I get here? I will get the equivalent capacitance. Let's call it C1. How will I find it? The potential difference. The outer shell is grounded, so let's call it B and let's call it A. So VB is grounded, so that is 0. VA is going to be self potential is KQ by A, and because it's in the interior of B, I'll get minus KQ by B, correct? So what is VA minus VB? That is just equal to this VA. I'll write K as 1 by 4 pi epsilon naught. Q also I can take common. I'll get 1 by A minus 1 by B, correct? So what is this? Let the potential difference be V. So I'll get V is equal to Q by 4 pi epsilon naught. I'll get AB and B minus A. Now, if I rearrange it, I can write Q by V, which is nothing but the equivalent capacitance, right? Let's call it C1, is equal to, what will I get? 4 pi epsilon naught AB by B minus A. Correct? You would have done this in your class. Now, let's look at the case where I have an inner shell which is grounded and I have an outer shell given with some positive charge Q. Right? So let's say this is positive Q and the inner shell, let it have some charge Q. I don't know what that charge is at this point. Let's say the inner radius is B and the outer radius is C. So now I'm looking at B and C, right? I'm ignoring the innermost shell. Perhaps I should place it at the center, but it's not really that important. Okay, something like this. Now, let's work it out. Let's say since the inner one is grounded, let's call it B and let's call it C, capital C. So VB is 0 now, same as in the previous case. VC, what is it? VC would be equal to potential itself, potential that would be KQ by C plus, because it is, wait a second, VB is 0, VC is KQ by C, correct? Now, what is VB? We can write in terms of Q and Q. I can write it as KQ by C plus KQ by B, which is equal to 0. So if I rearrange it, I can solve for Q is equal to minus B by C into Q. Okay. So I'll replace this Q with minus B by C into capital Q. What will I get? KQ by C minus KBQ, capital Q, by C square. Correct? I can write K as 4 pi epsilon naught, take Q common, and I'll take the common denominator C square. What will I get? C minus B. Correct? VC minus VB would be just VC. So that I'll take as the potential difference V. If I rearrange it, what will I get? Q by V equals to, let's call it C2, which is equal to 4 pi epsilon naught into C square by C minus B. Correct? We have these two results. You would have done this in your class, I hope. If not, you can see it now. Now look at this figure over here. The innermost and the outermost shells are connected, so they have the same potential. And your the middle shell is grounded, right? So these two have the same potential V and V, and this has a potential 0. So between V and 0, there are two capacitors. So you can consider these to be two capacitors in parallel between V and 0. Correct? Now, what is the equivalent capacitance for parallel combination? Now we can switch back to green. So I don't have to write anything. I already have the results. So therefore, C equivalent of the system is simply C1 plus C2. I can take 4 pi epsilon naught common. What will I get? C1 is AB by B minus A, and C2 is C square by C minus B. And that would be your answer. Okay? Don't worry about actual charge distribution on each of the shells. This Q need not be the same as this Q over here. Okay? So don't worry about that. Just look at the two cases separately and then convince yourself that this is nothing but a parallel combination between the capacitor between A and B and the one between B and C. And then you can simply add the two results. That fine? If it is fine, let's move on to the next problem. Okay. Right, let's move on. All right. I'll zoom this problem out because it's written in small letters. What is this? When I'm pressing this, okay, let me think. Oh, I see. Okay. Please solve it. I'll give you 3 or 4 minutes to solve it. Okay. Please work it out. Right, do we have anything? So the key word here is that L is much smaller than D, and the plates, it's given, right? This separation D is much greater than the, I don't know what happened. The separation D is much greater than their size, right? So the area of the plates or the dimensions of the plates is also much smaller compared to the separation between the capacitors. So that is a key term there. Yes, anyone? Okay. Q1, Q2, 2 by D square minus 1 by D minus L, is that? So use the fact that D is much greater than L, right?
Yes, sir. I was going to, but I just left without approximating.
Okay, sure. Let me see if that actually. But in the denominator, you're getting D square, right? Q1, Q2 by D square, basically the dimension of D square. Okay. Fine. Okay, so let me start the problem then. Where is it? So that's, like I said, the keyword here is this distance D is much greater than the separation between the plates and also the dimensions of the area of the plate also, right? Which means if I were to draw this, let's say on a real line like this, let's say these are the two plates, okay? They are very small and they are kept like this, okay? Both have the same separation. Here you have charge Q1, the other plate will have minus Q1. Here you have Q2 and the other charge will be minus Q2 kept like this. And the separation between them is D, which is much greater than the separation between the plates, which is L, and the area of the plates, okay? Or the square root of the area. D is much greater than square root of the area of the plates. What does this Q1 and Q2 separated by a distance L look like from this zoomed out view? It looks like an electric dipole, correct? So we don't need to worry about capacitors anymore. This is the dipole question in disguise. So you have two dipoles. How do you draw dipole? From negative to positive, right? So you have two dipoles. Let's call it P1, which is nothing but Q1 into L. And the other dipole, which is P2, which is Q2 into L, along the same line, right? Separated by this distance D. Correct? What is the field due to P1 at the second dipole P2? So we'll assume short dipoles here. So the field here PE1, which is due to P1, is nothing but 2K P1 by D cube. Correct. Now, the potential energy of the second dipole in the electric field of the first dipole, I can write it as P2 into E1, right? Both are in the same direction, so cos theta is 1. And let's ignore the minus sign for now. If you want, you can put the negative sign minus. Okay. So what will I get? I'll get minus 2K P1 P2 by D cube, or let's say this is some distance x. So that variable is x, and then we can put x equals to d later. X cube. Correct? Field into potential. So what is the formula for U? U is minus PE cos theta. The dipole, the field due to this dipole, it will be in this direction. That would be your E1. And the dipole P2 are in the same direction. So cos theta is just 1. So I'll just get minus P into E. Which P? The dipole 2 and electric field due to dipole 1. Okay. So what is the force then? Force is defined as minus du by dx. So this gives me, I guess we just need the magnitude. So don't worry about the negative sign. If I just write, I can get rid of this. I'll just write du by dx. What will I get? 2K P1 P2 by 3x to the power, sorry. So I'll get 6K P1 P2 by x to the power 4. Okay. 6K means 6 by 4 pi epsilon naught. P1 and P2, I can write it back as Q1L into Q2L by, now I'll put x equals to d. So I'll get d to the power 4. So what is my final answer? 3Q1 Q2L square by 2 pi epsilon naught d to the power 4. That is your answer.
Sir,
Okay. Yes.
if you don't take the approximation that take it as two dipoles, it should still work, right? If you take
It
them
might
as
work, but yeah, it'll be a much more lengthier problem, right?
I mean, I tried that, but I got something that was independent of L and D.
How would that be possible? You have
Like,
these dimensions.
I took the force between each dipole as q square by 2a epsilon naught.
Okay, but
And then between since the electric field doesn't depend on the distance.
no. So when we talk about that, see, that is not always true, right? That is only true if you have actually an infinite sheet of charge. So what we assume is for two parallel plates, the distance between the plates is very small compared to the dimensions of the plate. So this d is much smaller than square root of a. In that case, if you look at any point between the plates, it will almost, you can approximate it to an infinite sheet of charge. So in that case, you will get E is equal to sigma by epsilon naught, which is the constant, right? But when you're looking at these distances where it is much larger than the dimensions of the plate, this approximation will no longer hold. The field will depend on the distance. Okay. So you can approximate these plates now as point charges if this d is much greater than L and root of a. Okay, so that's what we are doing. We are assuming them to be point charges. So they just look like dipoles now. So the interaction between dipoles we have studied, we'll just apply that here. That's all.
Okay.
Okay, good. Any other question? I hope this is, so this is just a dipole question masquerading as a capacitance question. With the capacitance, it will be very much more complicated, right, if you try to solve it. All right, let's move on then to the next problem. Let us go to the next one. Yeah. I'll zoom this in. Please try to solve it. I'll give you 3 minutes to solve it. The clue is in the figure. I hope the figure is visible to everyone. So you need to find the charge on this capacitor, which is labeled as C here. Okay, this one here, in case that is not visible. Okay, anything? Do we have anything? Like I said, the clue is in the figure. Okay. You might wonder why are there labels given A, B, C, D, E, F, G, H. So can you follow those breadcrumbs basically? Then the answer will become very clear. I'll give you a couple more minutes to figure it out. Then I'll tell you. Okay, finally we have an answer. Yes, 60 is the correct answer. Okay, so let's see. Right, so this looks like a complicated circuit, but there are clues, like I said, hidden in the problem. It's not hidden, it's like staring you at in the face. Let's follow this ABCD where this is leading us. Okay, if I look at A, this is one terminal of the capacitor which we require, right? Let's use a different color for this. Let's use yellow, I suppose. So this is one end, and this is the other end of the capacitor, right? So let's say here the potential is A, okay, or let's say is X. We don't reach X, right? And let's look at point B. This side, let's say the potential is Y, right? The capacitor is between X and Y. Now let's follow X and Y and see where we end up. Okay. So if I move around, let's look at, let's start from B. Okay. So I'm going from Y to B. Remember, you will always follow the path of least resistance, right? The capacitance essentially has infinite resistance because there's no connection between the two plates, right? Once a capacitor is fully charged, it is essentially like a broken open circuit, right? So let's follow. I just have a conductor here, B. Then you go to C. Again, you come across just a conducting wire. Come to D. Then D to E. E to F, you can go this path, right? Move over here. F to G, you have a conductor. G to H is another conductor. H to I, J, and that's all, right? I don't have any other place to go. I'll just stop here at J. Okay. Now let's follow A. Let's use a different color for A. Let's use purple. Let's call it A. This is point as X. A to N. N to M. M to L. L to K. And that's it. Right. I have arrived at the terminals of a cell which has EMF 10. Right. This is 10 volt. which means if this point is x, so is this, so is this, so is this, and so is this. If this point is y, all these conductors means all these points have the same potential y, 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 and y. Correct. Between x and y, the potential is 10 volt because of that cell. And you have a capacitor, just one capacitor between x and y. So now you can solve the question, right? Your delta V is 10 volt and your capacitance is 6 microfarad. So what is the charge? 60 microcoulombs. Is this clear? You have these conductors here, so that means all everywhere will have the same resistor, same potential, sorry. Correct? Similarly, here also everywhere you will have the same potential. You arrive at the terminals of a cell. You know the potential difference is 10 volt. So apply the same potential difference across this given capacitor. Okay. So that's why those labels are given, so that you can follow those labels around and then identify what the problem is actually asking. Okay. Let's move to the next problem now. If this is clear, if you have any doubts, please ask. Fine. All right. Let's move on then to the next one. What is the next one? Okay. Zoom in on this one. Please solve.
So shortening means they close the switch, right?
Yeah. Okay, so SW is just closing the switch here. That's all. That's what shortening the circuit means. Shortening the switch means. Right. We have what response? They're not asking the current, they're asking charge. So it should be, in the dimension should be E times C. Right? Charge is voltage times capacitance. Let's see. Okay. And they're not asking the final charge. They're asking how much charge will flow through points 1 and 2 when you close the switch. EC2, 0. Okay. Okay, let's start solving the problem. Right. So initial we can write down, let's say when this switch is open, both the capacitors will have equal amount of charge because they are in series. So let's say that charge is Q initial. Okay. So Q initial on both Q1 and Q2 is just Q. Let it be. Correct. And you can figure out what that is. Basically, Q is equal to, the equivalent capacitance is just C1, C2 by C1 plus C2 times the potential difference E, or the battery voltage E. That is the initial charge. Okay. Now, once you close the switch, you have this potential difference E supplied to this cell, this capacitor C2. So that will fix the potential difference here as E. So the new charge on C2, let's call it Q2 now, would be C2 into E. And the new charge on capacitor 1 would be 0 because there is no potential difference. If I take this as 0 and this as 0, here I'll get E and here also E. That means between the terminals of this capacitor, there is no potential difference. So Q1 will be 0. Correct? But that's not what the question is asking. The question is asking, once you close the switch, how much charge will flow through points 1 and 2? Which means, let's assume, since this is in the left branch, let's say that charge that flows is Q1. Okay, small letter Q1. And the charge that flows through in this branch, let's call it Q2. Okay. And sum of these two charges, let's call it Q3. Okay. From the junction law, Q1 plus Q2 equals to Q3. What are these Q1, Q2, Q3s? These are the charges that are flowing once you turn on the switch or once you close the circuit, close the left side of the circuit. These are not the final charges on the capacitors. Final charges we just found out. It is 0 on C1 and C2 times E on the second capacitor. That is correct. Now, in order to find how much charge is flowing once you switch it off, what you need to do is look at the differences. So initially there was some charge Q, which is given by this. In order to find what is Q3, the small Q3, basically what I need is Q2 minus Q should be equal to Q3, or I'll write the other way around. Q3 is equal to Q2 minus Q. The final charge, which is C2 times E, which is clearly greater than the initial charge, C1, C2 by C1 plus C2. So how did it get that charge? Some charges must have flown from the two batteries and then come to this plate of the capacitor C2, which is what I'm calling it as Q, small q3. I hope you're following. If not, please stop me if you have any doubt, if you don't understand something. Okay. So that would be the final charge on capacitor minus the initial charge. Let's write it down. What is this Q2 minus, I'll get C2 minus C1 C2 by, I can take C2 also common. So 1 minus C1 by C1 plus C2 into C2E. So this gives me C1 minus C1 will get cancelled. I'll get C2 square E by C1 plus C2. That is your, actually, I don't need to write it like this. Let's not write like this. Let's just write it like, let's just write it in the separate form. So that is C2E minus C1 C2E by C1 plus C2. Okay. Now, let's look at Q2. What is Q2? Same thing. Q2 initially had charge Q, which is given by this, and finally it has charge 0. C1 initially had charge Q, and finally it has charge 0, right? Is it correct? So what is Q2? Q2 is, we're looking at it in this direction. So I'll write down, it is losing charge. So I'll just write it as Q minus Q1. Or let's write like, sorry, I'll write it like Q1 minus 0 or minus Q. Okay. Again, final minus initial. That will give you how much charge it has lost. Okay. So what will I get? Q1 is 0 minus Q is C1 C2 E by C1 plus C2. So that would be your charge 2 through point 2 minus C1 C2 E by C1 plus C2. Okay, because it is losing charge. Now, from the junction law, you can write Q1 equals to Q3 minus Q2. Okay. So Q3 is C2E minus C1 C2E by C1 plus C2. Q2 is minus C1 C2E by C1 plus C2. So if you drew Q3 minus Q2, what will you get? Just the first term, C2E. And that is your Q1. So these are the two answers.
Can you repeat how you got Q3?
About?
Can you repeat how you got Q3?
Yeah, sure. So Q3 is how much charge is flowing through the capacitor so that the capacitor goes from initial charge Q, this one, to final charge, this one. Okay. See, initially your capacitor had some charge Q. Now, the circuit pumps more charge into it so that it now becomes Q2. So how did it go from Q1 to Q to Q2? There would have some charge flown from the circuit, which is what I'm defining as Q3. So what is Q3? Final charge minus initial charge. Got it? That's what I've written, Q2 minus Q. Okay. Similarly, this small Q2 is the same thing for the first capacitor, C1. So final charge minus initial charge. Final charge we found out is 0 because there is no potential difference. Initial charge we knew, so the difference gives us Q2. Now from the junction law, Q1 is nothing but Q3 minus Q2. So when I take the difference, I'll get the charge that is flowing in this left branch immediately after turning on the switch. Okay. So those are the answers. Charges through points 1 and 2. Fine. We have about 15 minutes left. So let's try to solve a few more questions. Let's go to the next one, if that's okay. Fine. So all this, I'll post the notes. Please work out the problems and the ones we are not able to do. That was also you work out. You have any doubts, please post it in the doubt session so that others can also benefit from that, right? And you can start a discussion. Please use the doubts group. Not a single post I have seen so far. Okay. Any doubts for whichever questions, those we are not able to cover in the class also, please feel free to post it there, or any questions from anywhere. Okay, and let's have a discussion. Right, let's move on to the next problem now. Okay, this is just calculation, but you can try it. I'll zoom in. You try it for 4 minutes, let's say, right? First part, and the second part just follows from the first part itself. So it's just calculation. There's nothing special about this problem. Okay, so the expression might be lengthy to type out. Let's just start the solution. And please stop me if you have any confusion or doubt. So the permittivity, so they say dielectric constant, but it's actually permittivity that varies. Okay. So you know that in general we write permittivity as the relative permittivity into the permittivity in vacuum, right? And this relative permittivity is also called the dielectric constant. Here that is not the case. Here they have given permittivity as the vacuum plus some constant times x. Okay, so there might be some confusion. Your answer may vary due to a constant. So let's not write this as the dielectric constant, but as a permittivity itself. That's one point. Now, in general, you know that, let's say this is some dielectric, we can write if you have some field in a region, right? With the introduction of a dielectric constant K or dielectric with a constant K, the field reduces by a factor of K. Okay. So in typically, let's say you have a parallel plate capacitor. Let's draw the figure here. You have plus Q and minus Q. I'm assuming, unless it is mentioned, we will always assume the capacitor to be isolated. Okay. There is some, let there be some field. That means there is some charge on the plates of the capacitor. So there will be some field. Let's say the plate area is A. So I'll get the initial field, let's call it E naught, to be equal to Q by A epsilon naught, right? Sigma by epsilon naught. Now, there are dielectrics for, so this is 0, x equals to 0, let's call it. And this is x equals to D. And this is x equals to D by 2. Okay. Let's call this as E1 or epsilon 1 and epsilon 2 for the second region. So from 0 to D by 2, you have E epsilon 1, and from D by 2 to D, you have epsilon 2. Okay. So field in the first region, let's call it E1, capital E1. I will write it as Q by A epsilon 1. Correct. And the field in the second region from D by 2 to D, I will write it as Q by A E2. Correct. And where we can substitute what is E1 and E2, which is E naught plus beta x and E naught plus beta into D minus x. Okay. So this gives me Q by A into epsilon naught plus beta x. And similarly, E2 equals to Q by A into epsilon naught plus beta into D minus x. Correct? Those are the two fields. How do I write the total potential difference? Delta V, I can write it as minus integral of E dx. Right? Everything is in the same dimension, so we don't need to worry about the dot product. Let's write it as 0 to D. I can break it into two integrals. I can write it as minus 0 to D by 2 of E1 dx minus D by 2 to D of E2 dx. Okay, let's write it down. So this will give us minus Q by A is a constant, integral from 0 to D by 2, 1 by epsilon naught plus beta x into dx minus Q by A into D by 2 to D of 1 by epsilon naught plus beta into D minus x into dx. Okay. Before I solve it, let's look at the second integral here. If I do a change of variable, let D minus x is equal to t. Okay. In that case, what will you get? You will get minus or dx is equal to minus dt. Correct. And your limits will change from when x equals to d by 2, you will get t is equal to d by 2. When x is equal to d, you will get t equals to 0. So this second integral becomes d by 2 to 0 minus 1 by epsilon naught plus beta t into dt. Right? Minus comes from this minus dt. If I flip the limits, basically I'll get 0 to d by 2, 1 by epsilon naught plus beta t into dt, beta x into dt. No, correct. Beta t into dt. Correct? But if this t is a dummy variable, right? I'm integrating over that variable. So whether I write t or x, it doesn't matter, which means it is identical to the first integral. So therefore, I can replace the second with the first one. So this just becomes 2 times of the first integral. So continuing from here, I will get delta v equals to minus 2q by a into integral 0 to d by 2, 1 by epsilon naught plus beta x into dx. Now this we can integrate easily. I can now make a change of variable, let it be equal to u. So I'll get beta into dx is equal to du, or dx is equal to du by beta. Okay. So I'll get minus 2 by a. I'll put the limits later. I'll get 1 by u du with a beta multiplied down here. This integral everyone knows is just natural log of u. So minus 2q by beta a into ln u. Substitute back what is ln u. I'll get minus 2q by beta a into ln epsilon naught plus beta x. Between the limits, now I'll put the limits 0 and d by 2. Correct? So let me add another page here. So what is this? After plugging in the limits, again, delta v, when we're doing positive, we are going from positive plate to negative plate, right? So this delta v is actually v minus minus v plus. So if you do v plus minus v minus, what will you get? You will get 2q by beta a natural log of upper limit divided by lower limit gives me epsilon plus beta d by 2 divided by epsilon naught. Or finally, I can write down, let's say this is equal to v. Okay. So v is equal to 2q by beta a into ln 1 plus beta d by 2 epsilon naught. We got the total potential difference between the positive and the negative plate. Now, as you always do, C equivalent is q by v. So if you do q by v, you will get beta a by 2 ln 1 plus beta d by 2 epsilon naught. That would be your capacitance between the plates. Okay. Once you have the capacitance, let's just finish this problem and end it. Once you have the capacitance, you need to find for what value of beta would the capacity of the condenser be twice of that when it is without any dielectric. So without any dielectric, basically you will get C equivalent is equal to, without any dielectric, it's just 2 into epsilon naught A by D, right? So equate it to this over here, beta A by 2 ln 1 plus beta D by 2 epsilon naught. I can cancel A, and that's the only thing I can cancel. I'll write down beta equals to 4 epsilon naught ln by D into ln 1 plus beta D by 2 epsilon naught. So this is an example of a transcendental equation. Right? Which means its analytical solution is very hard to get. One way to get this is through numerical, just by graphing it. So on the left side, you have, let's say, y equals to beta. On the right side, you have y is equal to some constant times the logarithm of this function of beta, right? So you draw the two graphs, see where they're intersecting, okay? One trivial solution you can find is beta equals to 0. You substitute beta equals to 0. What will you get? Left hand side is 0. Right hand side would just become ln 1, which is 0. So beta 0 is a trivial solution. And there's a non-trivial solution which approximately gives you around 5 point something, right? But don't worry about that non-trivial solution. In your DPP also, the answer is just this equation, right? It's a transcendental equation. Okay. So you don't actually solve for beta. You just arrive at this equation and that's it. Okay, so I think we're out of time. Next few questions are actually simpler, I believe. There's one, this question is good. You try this one. And yeah, these are all good questions. So if you have any doubts, please feel free to post it in the doubts group or in your regular group, wherever it is. Okay. Let me or other faculties know about your doubts so that we can clear them. Okay. Vaishnavi, you had any doubts, please post it now itself in case you forget. And then I can get back to you. Okay. Okay, so everyone, thanks for staying back. I will see you all next week. Next week, we'll do a different DPP, I think. Current electricity probably, or if not, we can do class 11th topics if we haven't covered current electricity up to that point. Anyway, have a good night, everyone. See you next week.
Thank you, sir.
Thank you, sir.
Thank you.
Bye.
Thank you,
Thank
sir.
you.
Thank you, sir.